Hi, as the previous slide said, I'm Nick Chadwick. I'm a software engineer at Mux, and for about the past 10 years now, I've been working in some way, shape, or form with RTMP and live video over the internet. Today, I'm going to give a talk targeted at two different audiences kind of at the same time, so I apologize if I'm retreading any ground that you've already heard before. I'm trying to target this talk at WebRTC engineers, hopefully like yourselves, who want to learn a little bit more about how you can integrate WebRTC flows with traditional broadcasting workflows. And I'm going to go over what a traditional broadcasting, I don't mean going over a satellite truck and over a TV, I mean over the internet, but kind of the workflows that sites like Twitch or Facebook or YouTube are using right now to deliver great live video experiences over the internet. I'm also targeting this talk at live engineers working in that model who want to learn a little bit more about integrating with WebRTC and why you should learn a little bit more. I think there was a great note at the keynote this morning about how more and more WebRTC workflows and live broadcast workflows are coming together and being the same thing. The experiences that we're trying to develop are the same. And today I'm trying to give a talk to try and help us bridge that gap. Okay, so I'm going to go over how traditional RTMP and HLS live streaming works, just to make sure you have a firm reference of the model. I'm going to go over very briefly and very lightly the WebRTC model. Now, I'm not going to go into much depth here. I'm not going to talk about things like selective forwarding units. I'm just going to go over the key pieces of information that you need to know if you're wanting to bridge that gap to a traditional live workflow. I'm then going to talk about why we really need to start bringing these models together. I got the slide slightly wrong. And then finally, I'm going to give you a practical approach with hopefully a live demo that works of using WebRTC in a live broadcast workflow. So let's start with what the current state of the art is for going live over the internet. And there's two key protocols, RTMP and HLS. Here's a diagram that describes how we currently go live. You'll have some source of live video, be it a camera, a mobile phone, or perhaps even someone playing video games at home broadcasting to something like Twitch. That raw source of video is then going to get encoded into RTMP. That's the protocol that's going over the wire. And inside RTMP, you're going to be using codecs like H.264 and AAC. You're then going to send that stream up to the cloud, where a cloud transcoder is going to create multiple different renditions of your content targeting different resolutions and bit rates for different users. It then gets packaged, and I'm talking about HLS primarily today, but you might also have heard of Dash, which is another segmented streaming format that's very popular. Finally, your cloud encoding solution is going to use some kind of origin serving before sending it out to a CDN. It's very rare that your technology solutions are going to get to the scale where you can run your own CDN. So it's best to leverage one that already exists. Your CDN is then going to cache your video and allow it to be served out to the various people who want it, be they on TVs, laptops, or phones. Let's dive in to how HLS actually works. And like I'm saying, a lot of these concepts apply to Dash, albeit with a slightly different format. Now, HLS came about really because of the iPhone. The old workflow was you would create a version of your video, you would put it on the internet, and people would download it. That had some limitations when iPhones were coming out, connecting to things like 2G or 3G connections or Wi-Fi, where the quality of the connection that the device had could vary quite a lot between how you were using it and specifically where you were using it. And that drove the creation of this segmented model originally. The way it works is you advertise a master manifest of your content. What this master manifest describes is the various different ways you're going to make your content available. At what resolution you're going to make it available, what bitrate, with what codecs. And each of those descriptions then has its own manifest describing specific segments of the video that you're going to make available for download. Now, the most important part about this technology is that each of those segments across the different renditions represents exactly the same slice in time. We'll get to why that's important in just a second. So let's dive into what a master manifest looks like with HLS. You can see here that there's some version headers, there's a note that we're using independent segments, and then in this trivial example, I've got 3 different renditions. I've omitted some of the more esoteric details to give you the 3 key details that each of these renditions has. It has a resolution, it has a bandwidth. Oh no, I messed this up. They're meant to have different bandwidths. My bad. And frame rates. And you can imagine that the 1080p might be 60 FPS, and the 360p rendition there might be 15 FPS. That would still be entirely valid if your presenter had done a better job of this slide. Okay, moving on to each of the rendition manifests. You might download, say, rendition 1 and rendition 2. And you might be surprised to learn that they look almost exactly the same. Now, this won't always be true if you're using non-relative URLs. You can see here that the 6.ts represents a relative URL to the rendition manifest. These 2 files would be different if we were using the full path to the segment. But what's important here, as I mentioned, is that each of these segments represents exactly the same amount of time, as shown by the extinf here. Even though the exact duration of each segment might vary, what's important for the spec is that the time frame matches across renditions. Now, you might be thinking, hang on a second, but you haven't talked about live yet. Well, the way that live video is expressed in this segmented world is through time having our rendition manifests change. Each rendition manifest in a live HLS broadcast represents a slice of time and several segments from that slice of time. And it's a sliding window. You might advertise that you have a target duration of 5 seconds and several segments in your manifest. Then, 5 seconds later, if you download that same manifest, you can see that our 6.ts has slid out of our window, but 10.ts has now been added. In that sense, this file represents a sliding window of time, and each of the segments represents one slice of time that you can download and play. This way, as long as you keep updating your rendition and downloading the most recent segment in that rendition, you can play a live stream. Now, there are some key features that it's important to understand about why this format came to be and why it is the way it is. Now, the first thing is that by having different renditions of our content, very similar to simulcast in Webrtc, you can support viewers with differing network conditions. If I'm on a poor 3G connection, I might only be able to handle a 500 kilobit download per second, whereas if on my desktop, I can handle a full 10 megabits. And what this format allows us to do is deliver the best quality that your device can currently handle. But then within a single device, within a single user session, doing this way enables clients to adapt to changing network conditions. You might imagine that you're wandering down the street and connecting to various different 4G access points with various different levels of congestion, which greatly impacts your device's available bitrate. And by advertising chunks that are the same representations of time, we can allow our client to dynamically decide whether or not it wants to download a good-looking chunk because it has lots of bandwidth, or a small chunk because its bandwidth is currently limited. Now, this requires us to have smart clients. Your client needs to be constantly testing how much bandwidth it has available to it so it can make good switching decisions between these renditions. But crucially, this technology worked with dumb CDN servers. The only thing you needed to get right in order to make HLS live streaming work was having a short time to live on your rendition manifest. As long as you could make sure that your CDN was updating your rendition manifest every few seconds, you could just use the technologies that they already have. It didn't require complex RTSP or RTP servers, or nowadays complex WebRTC servers, in order to do live streaming. You could use a straightforward CDN with distributed points of presence across the globe with well-known pricing. OK. Then the input format was RTMP. And RTMP is pretty much a mistake. And if you're wondering, OK, RTMP wasn't it that Flash thing? It was kind of like a predecessor to WebRTC. You're not wrong. And it kind of lives on in a zombie format. It's used by places like Twitch or Facebook or YouTube to go live. And I'm just going to go over some of the key features of RTMP right now. It is a TCP-based protocol. It supported bidirectional communications. It supported multi-stream communications. You could, in fact, in 2005, open your Flash players on 2 different sites and have a conversation with a friend in another country. That didn't work very well because it was TCP, but it did sometimes work. And it also included an RPC mechanism. And then time happened, and now the actual features are, no, we don't use bidirectional communications. We, in fact, only ever use a single direction to broadcast video over RTMP. Multi-stream communications, nah. We only ever do we only ever send a single stream over RTMP, one with a single video stream and a single audio stream. There's no backup second language here, no. And there's an RPC mechanism. Nobody really uses it because RPC is vendor specific. So what actually happened is RTMP ossified into the protocol we know and love today. And there's a list of audio codecs it supports. You might note that Opus isn't on it. There's a list of video codecs that it supports. And you might also note that it supports cutting-edge technology like VP6 or H.263 and that very experimental AVC/H.264. And it doesn't support VP8, VP9, AV1, HEVC, or anything else. OK, so that's what we use. Now, let's do a quick overview of the WebRTC model. And I know I'm giving a talk about the WebRTC model to a room full of WebRTC engineers. I'm sorry. I'm really, really sorry if I get it wrong a little bit. I'm just trying to get the high notes. OK, so it's a free open project. And its mission is to enable rich, high-quality RTC applications. And it's supported by some big names. And it is video chat built right into your browser. Yes. But it's also tools in an ecosystem for building experiences that leverage low-latency audio-video communications. And it's built using the best of what existed. And there's 2 separate tracks you need to be aware of when you're talking about WebRTC. The first is that there's the W3 standard for JavaScript. And when we're building web applications, this is what the model that we need to care about. But when we're building live video broadcast systems, what we really need to care about is RTC Web, which is the IETF working group for the low-level protocol. They do things like picking RTP profiles and specifying exactly how we're going to express audio and video to our other parties. OK, so WebRTC solves a fundamental challenge of being peer-to-peer. Now, what is this challenge, you might ask? Well, a traditional if you go to google.com at home, you are most likely going to, your network is most likely going to look something like this. You're going to have your computer behind your home router, which has a connection to the internet. When you make a request to google.com after you've done the DNS, I'm talking about the TCP packet that you're going to send. You're going to say, I know that Google is at 211.122.1.5, and I would like to talk to it on port 80 and make a request. And when you send that TCP packet, you say, oh, and this is the sender, it's me. But note that this is a 192.168 address. That's a local address. The internet can't talk to it. What your router does is sets up a mapping between your internal IP and port combination and the connection that you're trying to make out to Google. And it writes into the source its actual public IP address. Then when Google responds, it says, OK, well, I'm Google. I'm sending this packet, and I'm sending it to this public IP address. Your router then looks up in its mapping which local connection that packet should be sent to, rewrites that TCP header and says, OK, here you go. Now, this works if you are connecting out, but it poses a fundamental challenge if we're trying to talk to each other. And that challenge is solved by what's called ICE. Now, let me try and explain briefly with a diagram. I'm sorry, I forgot where I stole this diagram for. If you're the author of this, thank you. What happens is we're both behind this network address translator. And that means that if I knew your IP address, I could send a packet to your router. But your router wouldn't know what to do with it because that mapping hasn't been set up for your connection yet, certainly not to me. And likewise, you can't send a packet to me. We could maybe go into our routers and set up port forwarding like you had to do to get some old video games working back in, nope. But if we have the ability to use some kind of reliable third-party signaling server, what we can do is use the stun protocol to find our public IP addresses, then exchange those public IP addresses with each other, and then we can both send a packet to each other. One of them probably won't get through, but it will be enough to establish that mapping in our routers. And then if we keep trying, eventually, we're going to get a connection through. And the way this is all done is through ICE. The way this is all done is through ICE, and that's why when you're looking at WebRTC messages, you need both a reliable signaling mechanism and you're going to see what's called ICE candidates flowing over the wire. But you also need some way of saying, hey, I would like to talk video with you and audio. And to do that, SDP was selected. That's how we describe the media that we'd like to exchange with each other. Now, there are experts in the room on this, so if you have any questions, please ask them, not me. But the very quick overview I'm going to give you is, it is defined by an RFC that existed long before WebRTC did. And WebRTC picked this because it's proven and it works, and it lets you integrate with legacy systems. And it looks a little something like this, which if you're a web engineer of any kind, you're going to be like, it's not YAML, it's not JSON, what is it? It's not even a protobuf. No, it's a custom protocol, and there's a lot of stuff in here which I am not going to go over at all. I'm just going to pick one of the really interesting features, which is we can describe the audio and video that we would like to send. But we can also describe the capabilities we have to send it and express a preference for which of those capabilities we would like the other side to use. And the mechanism that we use is an offer answer. We can say, hey, I'd like to send you audio and video. I can do Opus and some other codecs. I can do VP8 and VP9 and H.264. And I would like to use these codecs. And if you can't do that, maybe fall back to this, maybe fall back to that. OK. Then the other side can send an answer saying, OK, let's do this. Here's what I support, and here's what I'd like to do. Then when you actually start sending RTP packets over your ICE connection, both sides have negotiated what the media IDs in those packets actually represent in terms of codecs. OK. So I think I went over that. So now I'm going to talk about why our two worlds are on a collision course, if it wasn't already obvious to you. More and more RTC use cases are involving broadcasting. That was talked about this morning. That kind of experience where it isn't just me talking to one other person. It's often me talking to a friend, talking to another friend, broadcasting our conversation live, watching something else, having an audience write text chat back to us. There are all kinds of exciting use cases coming out here. And also, at the same time, the traditional live broadcast HLS world is focusing right now on how we can improve our latency. We're also trying to build these rich interactive experiences on top of the pre-existing codecs. Just last week, Apple at WWDC announced their new addition to their HLS spec called low latency HTTP live streaming. We're on a collision course. And as an industry, we're starting to hit some really interesting challenges. Like I was saying, we have these cool new codecs coming out, but also we have these cool new protocols coming out. This is SRT. I've grabbed a quick screenshot of part of the SRT raison d'etre. You can see here that it was created by Haivision and Wowza to power new, better live streaming experiences, to replace the RTMP part of our stack with something new and better. And you can see some of the challenges they're thinking about. They're thinking about jitter, packet loss, bandwidth fluctuations. They're thinking about how they can make it low latency. How can they secure it? By now, you should be thinking, hang on a second, I've seen this list of requirements before, right? This SRT is solving almost exactly the same problem that WebRTC is solving. Can't we just all be friends? Well, we can, but there are some challenges. The biggest challenge, as I see it, is that fundamentally the RTMP model is a point-and-go model. You open a TCP connection. You send some pretty well-defined packets saying, I would like to connect. I would like to publish a stream. And everybody's kind of standardized on, here's a stream key that uniquely identifies me and authorizes me to broadcast to this endpoint. And then you just start sending video over your TCP connection, and you're done. It's pretty straightforward to work with this. You can set up load balancers. We kind of know what to do with this. With WebRTC, though, there's a negotiation. And if you recall that diagram with the little cloud at the top, that cloud is empty because it is undefined. There is no well-defined mechanism of how you actually start a WebRTC connection. Once you have it, it's all well-defined. But how to start it is undefined. This is a challenge. Effectively, WebSockets are a de facto standard for this, at least when you're using web browsers. But it's still like, what is the message you're sending? How do you identify yourself? How do you authorize yourself? What is the packet structure that you're going to be sending? You need to send an SDP, and you need to be able to exchange, you need to send an SDP offer answer. You need to send ICE candidates, but how you do so is undefined. This is also a problem. There's no way to put Opus in RTMP. If you were thinking, okay, I'll just build some kind of adapter, well, the adapter you build needs to be able to transcode audio at the very least. And if you're using something like VP8, which is mandatory to support in the web browser, you can't just put it in RTMP. You need to transcode it into RTMP. There are also some other challenges around some of the complexities of WebRTC. Things we've been hearing about today at earlier talks. Talk about how the resolution that we're streaming at can change dynamically. The codecs that we're using can change dynamically. We can flip cameras around. We're not just dealing with an input of a fixed resolution. We're dealing with a very dynamic input. What if someone turns off their camera midway through your live stream? What do you do? How do you build applications around that? This is going to be a challenge. And the integrations we're going to build are going to be difficult. Now, to give you some inspiration, I'm going to go over 2 demos today of actually doing this integration. Although I have to admit up front, one of them doesn't work. So let me talk to you briefly about the first demo that I built. It totally works on my machine, but I couldn't get it working in the cloud. I built a demo called Webrtc Rebroadcast Err. It's designed to be the minimum surface area you can do to go live on a site like Twitch using RTMP, but have your input be WebRTC. And it exists as a transcoding rebroadcaster. OK, I built it using libwebrtc.a to power the WebRTC workflow. Libwebrtc.a is essentially what you get if you do the right magic on the Google official Chromium WebRTC project. And it's nice to use this project, or it's nice to have my thinking for using this project was, hey, it's the one everyone's using. Chrome's using it. I think Mozilla's using it. Pretty sure Edge is now using it. It seems like the default choice, and I should probably use it. Working with the official WebRTC source is awful. If you ever get to this point where you're like, I want to do something with WebRTC, I'm sorry. It is challenging. It's like a 10 gigabyte Git clone, and I was like frantically trying to build a Docker image and like trying to use conference Wi-Fi, and then my remote machine that I'm using for my demos today didn't have enough disk space to even unpack everything. I used boost.beast for WebSockets as I said, it's the kind of default. I use FFmpeg for converting the frames, and a very simple Python server to serve up some static HTML, do a connection, and be the WebSocket server in the middle. Now, I promise I'm going to get this working. You can take a look at the code here. Let me just it's under muxsync Webrtc Rebroadcast Err. It uses CMake. I've checked in a libwebrtc.a and a JSON-cpp.a to ease your integration. And if you want to check out the code, you can see things like the transcoder.cpp, which, oops, picked the wrong one, transcoder.h, which implements a video sync interface and an audio track sync interface from libwebrtc. And I've tried to create a Docker file which totally worked on my machine once, but just needs a tiny little bit of love. So if you're interested in trying this project out, please check it out. And I'm going to get it working soon. OK. So this was meant to be a demo of a very, very basic workflow. And then I was like, let's go crazy with something that probably won't work. And this is why I was kind of throwing libwebrtc under the bus. Because the next demo I'm going to do is for a more complicated workflow. OK, let's imagine you want to support two people from their phones having a conversation. And maybe there's some viewers who can chat with them, send them little messages, or love hearts, Periscope style. You're like, great. But then you run into this question. It's like, well, whose screen should I broadcast? Like, I don't want to broadcast either of these screens. I want to do something more complicated. I want to broadcast something like this. I want to have both of them get equal weighting, and maybe there's some intro when they come on. Maybe there's a ticker down the bottom. Let's go a little crazy. And you're thinking, OK, well, I can start with libwebrtc, and I can build some kind of compositing engine, and I'm going to have to do like layered effects. Maybe I can pull something off the shelf. Tickers and remote data integration, yeah, that's going to be a challenge. Wouldn't it be great if I could just use Chrome? All right, let's try another live demo of using Chrome as your server-side rendering engine. Now, this one totally worked earlier. So please bear with me. I had the picture of Da Vinci's ornithopter there because that thing was never going to fly, but we're all really impressed with him for giving it a shot. OK, you're like looking at my workflow here. You're still in my Twitch stream key. Please don't. Please don't. OK, so I'm going to log in as Alice here. OK, don't go to this URL, please. I beg you. I'm going to try this on my phone, so I have a second camera. OK. OK, I'm going to connect. I'm going to start a call to myself over conference Wi-Fi. OK, cool. So now I'm talking to myself. This is great. I've got my phone. All you beautiful people out there in the audience, give me a wave. Cool. You've probably all seen this Webrtc demo before. And here it is live on Twitch. Wow, the demo worked. Cool. And here we have Chrome being our server-side rendering engine. You can see that we've got some crazy effects coming on. There's transparency there. There's just this ticker down the bottom, which is all static. And if you're interested in exploring this technique for building rich, engaging live streams a little bit more, firstly, don't use any of my code. It's awful. But also, if you want to check out this technique, you can check it out here. It's open source. And you can see that there's a simple entry point here, running some stuff, Pulse Audio for audio, XVFB for off-screen rendering. And I'll go back to my presentation now. This, and this is a screenshot in case that demo didn't work. And yeah, this is a really fun technique where you can kind of use and abuse Chrome as your server-side component of your live streaming WebRTC infrastructure, because it has a lot of the things you're already going to need in order to go live. And like I said, this code is available. packaged up in a Docker file that does work and ready for you to have some fun with. OK, so this is open source. You can head on over to GitHub muxinc. My employer was very gracious enough to let me open source these 2 demos. And thank you so much for your time.